All right, let's get started. Okay, so I said, anyone have trouble finding the course website? Well, all I put in Brightspace was a link to the real course website. But is there any questions that I can answer regarding various class policies? Yeah.
Is there like an entry code for the grade scope?
Yeah, it should be there, hopefully. Maybe somewhere under the homework section or something about grade scope. Otherwise, Brightspace should have added most of you automatically. And I can press sync again for those who have added late. But hopefully there's... Okay. Other questions? Yeah.
Under the homework on like the collaboration section, there was a sentence saying about like we're allowing up to 3 person per submission.
Yeah, the homeworks can be submitted in groups of up to 3.
So each group will submit the same homework to 3 different grade scope accounts?
No, Brightspace should let you select multiple students.
Actually, I just have no such sections. I only got through like secondary student health and success and university.
Sorry, please say that again?
The Brightspace section, it seems incomplete for me. It only has 3.
Yeah, don't look at that. Go to fundamentalalgorithms.com/randomized. Yeah, I have no idea how to use Brightspace. And everything will be there.
Yeah.
So something I forgot to bring up last time. Do you guys want like a piazza kind of thing? Okay, so I've asked the TA to set up a piazza, but I should warn you that I will personally never check it. But the TA will monitor and help answer basic questions, but mostly it's for you guys to discuss amongst each other. I think it's fair to ask the TA only to kind of check during weekdays, not on Sundays and Saturdays and stuff like that. So you'll maybe check in the afternoon once a day or something like that. All right, so don't expect too much from the poor TA on the weekend. I'll also add that the website has been updated to show that our TA JD will have his office hours on Wednesday at, I think, 10 in some room in Haas, but you'll see it up there. The homeworks are due on Wednesday, so hopefully that'll be useful. Any other questions? Yeah?
Do you post these lecture slides?
Yes, I do. So at the end of every chapter, which corresponds to a lecture like you've seen, there is this thing called lecture materials. And you'll find links to slides. Both, when I prepare these, what I do is I usually write kind of the full version with everything written in, and then I go through and I erase some stuff so we can do it together. So I kind of post that first version with everything as well as the version that we make together. You'll see too. That's also where I'll post a link to the recorded videos of these lectures when I do it sometime this week. Other questions? All right, let the fun begin. All right, so what did we do last time? So last time was our introductory lecture. We really talked about the 3 applications, 2 in detail. FreeSat and Quicksort, we did some proofs and analysis for. I ran out of time to do the high probability proof for Quicksort. That's fine, please read it. And Quickselect, you get to play with on the homework. And then we went through an infinite number of definitions as well. So just to briefly remind us again, what did we do for 3SAT? Okay, 3SAT's some basic problem, but we're talking about trying to get approximation algorithms for 3SAT. In particular, we first analyzed like a silly algorithm where we just flip coins for everything. And we showed that got a 7/8 approximation, but the key point was to use linearity of expectation, which suddenly made everything easy because each clause can be analyzed separately. And the other thing we did was we talked about how to turn that completely random algorithm into a deterministic one. And the idea was to use this method of conditional expectations, where, okay, I have some random experiment, which I know is going to be pretty good, and then I can break it up with conditional expectations, say, oh, condition on the first one being heads, or the condition on the first one being tails, and at least one of those conditional expectations had to be good, and that's the one we would choose deterministically. But to make it a full algorithm, we also have to be able to evaluate the conditional expectation on the first one being heads, and the first one being tails. You know that numerical value, but luckily we can, again, sort of do a linear data expectation, and that, oh, if I set x1 to be true, I know the probability for each cloud, I can calculate that. So you can get kind of these scores, and you can choose the variables one by one. All right, so that was one thing we did. The other thing we discussed was sorting. We only had time to talk about the average case running time, but that's fine. That was really the main point anyway. And maybe it's although it is sort of a divide and conquer algorithm, trying to do a recurrence relation it is doable, but it is more complicated. And the trick that made it much easier for us was instead to figure out how to set up the appropriate indicator variables, we had a variable xij that told us whether or not element I was compared to element j, just said 1 or 0. And so if I sum up all the xij's, that gives me the total number of comparisons in the algorithm. That's roughly the running time. Okay? But what's great is once I put it in this format, once I look at it in this way, then really the key step is just to apply linear expectation and say, oh, the sum of these variables is the average of the sum is the sum of averages. In which case, I only then have to focus on, here's two elements, what are the odds of them being compared? That was like, if it was like between 10 and 100, it should be roughly like 2 and 90 or something, because it's whether either of these elements gets picked before anyone in the middle, right? And then you just sum it up. And it's the kind of sum we do all the time in computer science. Okay. But the real key point was to figure out how to kind of look at it in the right way that makes everything much easier. Okay, so those were the main keys last time. All right, today's a fun one. This is actually the lecture I used as the first one a couple of years ago, because I really like this application. So it's about a problem called heavy hitters in frequency estimation. And it's going to be our first use of hash functions. You guys have at least heard of hash functions before, because I'm sure you guys exclusively use dictionaries in Python. And we will actually get to use Markov's inequality today, which we talked a little bit about last time. We were supposed to use it for the high probability bound, but we didn't have time. So I'll do a quick refresher on that. Okay. All right, so let me motivate the setting. Okay, so have you guys seen this page before? You can go to like trends.google.com or something. It's sort of an interesting web page that sort of tells you what are sort of the high traffic things over time or right now. So, for example, I looked this up maybe an hour or two ago. This is what they say is recently trending on Google. As usual, it makes me feel old when I don't recognize some of these things. But as I understand, Nick Cannon is having another child, which is like 200 or something. Patrick Beverly got traded to the Lakers. Do you have any basketball fans here? Got 1.5. Great. If you really like basketball, another guy named Chet Holmgren is also out for the year. He's like 7'3" and his foot is screwed up, so he's done. LeBron James. Yes, yes. It took one play. LeBron James ran into him and then he broke. I guess there was also a soccer game today. Any soccer fans? 2 soccer fans. 3. Okay. Any sports at all? Okay. Fine. I don't know why Sylvester Stallone is in the news, but it's never good. And I don't know who Tyron Smith is. Okay. All right. But some level, okay, Google's sort of keeping track of what's popular and what's not, right? Okay, so why do they do this besides for our amusement? Okay. So tracking these popular queries is also very important from a caching point of view, right? You type something into Google and it comes back to you instantly. Why is Google so fast? Because someone else already made the same search as you, right? And they've already saved the answer, or something awfully similar, right? So a huge, just an overwhelming amount of traffic is coming from a very small minority of search queries, up to some, synonyms and stuff like that. Fine. But the amazing kind of question is how do you do it, right? Because queries are so open-ended. You can type anything into the search, right? So they potentially have to keep track of, I don't know if there is a number to limit the number of things that can be searched, right? Any string. And they certainly get a very diverse set of queries, even if many of them come from a few. That doesn't limit how many different queries there are. Okay. So at some level, how can they keep track of what is the most popular and get some estimate of how many times things are being searched when you don't have space to maintain a counter for every phrase in the English language? That's sort of a high-level question. Okay, what's up next? All right, so that brings us to this problem of heavy hitters. Okay. And we are going to look at a model called the streaming model. Okay. All right, so what's the idea? In the streaming model, okay, whatever input we're taking in, the elements are presented one by one. Okay, like I guess from a stream. So I guess this is a stream of letters in the alphabet: A, B, C, D, A, E, whatever. Okay, but the point is, you're like a computer, and you look at just one of these things at a time. Okay. And as these elements come in, for this kind of problem, I'm interested in identifying the quote-unquote heavy hitters. Okay, so if I said like the 5% heavy hitters, that means I'm interested in all of the elements that appear at least 5% of the time in the stream. Okay, so for that query analogy, the stream is just different search entries coming one at a time. All right, so it doesn't have to be 5%. We're going to study sort of a general parameter epsilon. Epsilon could be 0.01, 0.02, whatever. And we'll figure out some dependencies as a function of epsilon. Fine. Okay, so now what makes this problem easy? Again, because if you had all the space in the world, it's not very hard to figure out what is the most common, right? We would just write down everything and maintain counters for everything that appears. Okay? So what we want to imagine then, the reason we're looking at it as a stream, is that we are a small computer, very, very small compared to that length for the stream. You can't just write everything offline and just batch it or something. Okay? So we want to try to identify all of the heavy hitters with sublinear space. Okay, something less than the total number of possible keys. Okay, so, that's really the key point and what makes this problem interesting and also very practical if you can pull it off. Right? So, I guess for example, let's say that all the elements are integers between 1 and 9. The bit codes maybe integers, right? So the bit strings. So maybe if you can get square root n space, it's still kind of a lot, but it's a lot less than n as well. Right? More dramatic would be something like log n space. Right? That would be fantastic. I mean, you need log n space just to write down the ID of one of these things, so that seems to be pretty close to as good as possible. Okay. All right. And again, yeah. What makes a problem fun is that we can't just record all the counters in a dictionary. Okay. Any questions? Okay. All right. So, how is this even like plausible, right? How am I going to, at some level, figure out a ranking, in some sense, of a gazillion items in a very limited amount of space?
You can map them into a subspace. I mean, you can categorize some of them together.
Okay, you can try to you can have a thesaurus and group some together that are similar or something. But let's say it's still quite a lot of keys after that. Yeah.
I'm going to try a silly algorithm where, what if instead of counting up everything, I'll just randomly pick a few. And since it's heavy hitter shop often, I should be picking those.
That is a reasonable idea. Okay, so can we sample from the stream? If I'm only interested in things that are showing up 5% of the time, then if I sample 20, I'm hoping that it shows up once. And if I sample 100, it would show up 5 times or something. Okay, that's actually reasonable, and that will do okay. But we're going to actually do a little bit better if you have word calculations than that. Okay, I want to make a few high-level points. So, okay, one is this basic issue of how can I keep track of a gazillion counters, right? But maybe a follow-up question then is, at some level, how many counters, if I'm only interested in the 5% heavy hitters, how many counters do I need in like a limited sense? 20. There's really only 20 heavy hitters out there, right? So if not only am I trying to identify all heavy hitters, but I also wanted to count roughly their values, I should need maybe at least 1 over 5%, 1 divided by 5%. So that's one saving grace, is that actually the input's huge, but the output is not necessarily huge. Of course, the hard part is we don't know which it's going to be a priority. Okay. Fine. And now there's 2 other angles that we're going to take advantage of to make this problem tractable. Okay. One is that we are going to use some randomization and allow for a small probability of error. Okay, so at some level, trying to do this problem perfectly is going to be impossible. Okay? But if I'm just happy being right 99.9% of the time, that 0.1% of wiggle room is worth quite a lot. Okay. And the other thing we're going to do, okay, is that we're only going to try to approximate this problem. In a sense, I'll make more precise in a moment. Okay. So maybe like I want you to give me all the 5% heavy hitters, and you're allowed to accidentally give me some 4% heavy hitters as well. I'll allow a little bit of wiggle room. It has to include all of the 5% heavy hitters. Okay? But that wiggle room, again, is going to be very important for us to make this problem tractable. I think if you're trying to do this exactly and never make any mistake, there's nothing you can do but keep track of everything. So it's important to kind of adapt and have a slightly more open mind to do these amazing things. Okay. All right. So, all right. That's the teaser. That was the warm up. Here again comes some definitions, but it's going to be much shorter this time. Okay. So, what are the tools we need? I know we talked about this last time, so I only left this here as a reminder. So, remember Markov's inequality. If you have some non-negative variable x, or the odds of it being twice bigger than its average, at most half the time. Otherwise, the average would have to go up. In fact, that's the only version we'll need today, just the 2 times as much. Okay? But of course, that can be generalized to 3 times as much, or 1.2 times as much, etc. Okay. Now, the new one we'll need, but you maybe have seen to some extent before, is the idea of hash functions. Okay, so what's a hash function? A hash function is going to map, say, the numbers 1 to n, which could be bit string, so n could be big, to generally a smaller set of integers, k, And we want to do it in a way that kind of looks random, and we'll make that more precise in a moment. Okay? But at a high level, I'm mapping all of these items to different slots down here. Okay, so it's a function that just takes a number and outputs a number. But we're particularly interested in the case when the output space is smaller than the input space. Okay? I'm guessing many of you have seen this a little bit before. Okay? Since the output space is smaller than the input space, you have to have collisions. You have to have a lot of collisions. And that's what a collision is. You guys know what a collision is? Great. Okay, so, and maybe one thing to point out was these hash functions. They're random in the sense that the way we make them will be random. I'll give an example in a moment, but maybe you'll flip some coins and come up with a function, and then it's fixed forever. Okay, so the randomness enters in the construction stage of these functions. The functions themselves, when you're calling on them, they're not flipping new coins after that. Okay. All right, so the most kind of ideal hash function, and probably what you have in mind most of the time, is when for every key, I choose one output completely randomly. Okay? So this is called an ideal hash function, among other names. And it means that for each index I, I'm choosing hi kind of independently and uniformly at random. Independent and uniformly at random. So they have nothing to do with each other. And often when we're trying to design algorithms, this is the easiest one to keep in mind. Right? You might try to just imagine you had one of these, come up with some ideas. Assuming this kind of. Okay. But it's not actually useful. Okay, what's the issue with an ideal hash function? All right. Okay, so let's say think of n as being really, really big, and k also as being pretty big. I want to argue that I need a lot of space to write down an ideal hash function. How can I make that argument? Yeah.
If it's truly random, you need to just store what key you store than any other.
That's exactly the intuition, but now how do I sharpen it and kind of write down more of a proof-ish thing? Yeah.
No collisions?
No, there's going to be tons of collisions just because k is small. As soon as k is smaller than n, there's tons of collisions. It has to be the case, right? It's one of these. Yeah.
The thing, you have to independently define what each element maps to, because otherwise, if you change one element, then it becomes a different hash function.
Okay, so let me decouple this a little bit. So I think the way I described ideal hash function, you're not actually imagining me picking out a number for each one. So let me change the definition slightly to be a function h that behaves as if you had picked it out one by one, but maybe it was constructed in some other way, right?
You have to write the mapping for all n things. Writing all.
Yeah, but the question is, why can't I write the mapping out in some clever compressed way?
Because there's
Intuitively, there should be no pattern and stuff to take advantage of, right? But now, how do I kind of sharpen this? Okay. Now, if we're looking at ideal hash functions, then I think it's clear that any function from n to k is possible. Right? Anything is possible, like Kevin Garnett. Okay. But how many, then, possible functions can we generate? N to the k? nk. Okay, so there's a, okay. So you said nk? nk possible functions from n to the k? Okay, I see some no's. Any other guesses? Yeah.
K to the n.
K to the n. So okay, so why?
Every single number can be
Okay, so yeah, every input is another k choices, k choices, k choices, k choices, so you get 10. Okay, now, if I'm going to write down these functions, each of these k to the n must be described by a different bit string. Okay, so how many bits do I need to distinguish k to the n things?
2 to the power.
Okay. So we'll need log base 2 of k to the n. Okay. So we need n log k space, and in particular, that is again the space of writing down a number for each of these. But this is just formalizing the argument to give you a real space. So we have to distinguish between n to the k things. So you need log of that many bits, just to give everyone a different name, a distinct bit string. And for us, n is all the possible queries in the world, right? So we don't want to. So mathematically, this is the nicest thing, right? When we're doing analysis, it's the nicest thing, but it's not practical either. Okay, so maybe when you do an algorithm, you might just pretend you have this, and then we'll talk about more limited classes of hash functions that are just barely random enough to get what we need. Okay, so today, we'll be using something called a universal hash function, which is the kind of the weakest useful hash function. And so as opposed to guaranteeing that everything is completely random, okay, all I'm going to say is that for any two different keys, I and j, okay, so if two keys were complete, if just the two keys themselves were completely random, what would be the odds of them colliding if they're mapping into one of k slots?
1 over k.
1 over k. So that's the only guarantee you get for a universal hash function. It doesn't even promise you that I is going to be uniformly or random among it. But it just says that any two distinct keys have sort of that ideal chance of colliding. Okay, but only two at a time. It says nothing about how three keys are distributed together. And stuff like that. And later lectures will use slightly stronger hash functions which talk about 3 keys or 4 keys or 5 keys. Right? Sometimes more complicated things require stronger hash functions. But today we're only going to use universal hash functions where I'm only concerned with 2 keys colliding. Okay? And so here then is an example. Okay, so it can be a very simple function. It's just ax plus b modulo a prime, just to make some math work out, and then modulo k. Okay, so you do your ax plus b arithmetic modulo some large prime, like mod 5 plus b, right? And a and b are sampled randomly. A is sampled from 1 through p. B is sampled from 0 through p minus 1. Okay, so you don't have to write down very many bits, right? This is like log n bits and log n bits, right? Log p. Yeah, question?
We sample for hx and
No. So you sample just a and b once, and then you have your function. And that function will be used and applied to all x's. Yeah. So this probability up on top is before a and b are revealed. Yeah. All right, so keep in mind that we're going to be using a very simple function, and you can imagine this is very fast for a computer to compute, and very small to store, and very practical. Right? As simple as I can imagine, really. It's a famous thing that if you don't put mod p, you actually get some weird things going on. Okay. All right, so that's what we're going to use. All right, so those are the two tools we're going to come up: Markov's inequality and universal hash functions. All right. Any questions? Great. All right, back to fun stuff. Back to algorithms. Yeah.
so why would the
Why would it take k to the power of n space to do the truly random function?
This is just saying that if you had done a truly random hash function could take on any possible function from n to k. Now, how many possible functions are there?
Oh, so like it would take that much to write it out?
Yes. So because there's k to the n possible functions out there, and if you're just assigning each function a different bit string, you need log base 2 of k to the n. So the nice thing about this argument is that we're making no assumption about how the function's actually represented. Right? It's just doing a kind of counting. Every one needs a different bit string argument. All right, so with these tools in hand, let's go back to the heavy hitters problem. This is just the same slide from before. I want to get everyone that appears more than 5% of the time. Okay. Again, the fun part is figuring out how to do this without writing down all the counts. Okay. And so from now on, I'm going to talk about epsilon heavy hitters for a fixed parameter epsilon. So epsilon would be 0.05 if we were doing 5%. So it could be 0.01. You know, even making epsilon 1 over 1,000,000 or something is still pretty practical because you can keep track of 1,000,000 counters. Okay. Fine. So in addition to identifying the heavy hitters, there's a related problem also estimating their frequencies. Okay, so just some quick definitions. So the absolute frequency of some element x is the total number of times it appears. The relative frequency will be the total number of times it appears over the total length of the string. So that's the percentage. So, so actually the problem we're going to work on directly is trying to estimate the relative frequency of every element up to some fixed additive error of epsilon. Okay, so something that's an epsilon heavy hitter is something where relative frequency is at least epsilon, just to double check our definitions. All right, and it's a homework problem. I haven't decided whether to assign it, but at the moment it's left as an exercise to do the last step where you show how to take something that can estimate relative frequencies and actually properly output a list of heavy hitters. Okay. But we'll focus on the relative frequency formulation of the problem. Okay. So now we have a kind of a similar question to before. Okay. So before the question arose of how can I keep track of all these counters for 5% heavy hitters? Well, there's only 20 heavy hitters, so there is some hope. Okay. Here's maybe an analogous question for relative frequencies. So I give you some parameter epsilon, and I say, okay, I want you to estimate the percentage of each element up to, say, plus or minus 1%. Okay. And again, you have this issue of, I can't keep track of counters for every element. So I ask the same question again to you guys. So my issue is I want to get additive 1% error for every element. And I'm not allowed to store counters for everything. Why is there even hope for this? I guess hash functions, yes, but I was looking for a different answer. Or does the issue at least make sense? You know, that. What's the problem?
There's an error, so we can make guesses.
There's an error? Yes, we're going to take advantage of the error, but yeah, articulate that further.
You can say the element that close number of frequencies in the same hash. Like they collide.
Oh, so you're saying, can we bucket by frequency or something? But if you bucket by frequency, you're going to have lots of lists, no? I mean, especially the very small bucket is going to just have all the elements listed and stuff. Like, yeah, I guess questions are always posed a little awkwardly. Just Yeah.
Thinking if it allow up to 1% error,
Yeah.
does that mean for anything that shows up with 1% or less, we don't have to keep track, we can just assign 0 to them?
Okay. So the one saving grace then is that 0 is actually a good estimate for almost all the elements, right? Because only 100 of them can have actually at least 1%, which means the other infinitely many, 0 would have been a fine answer for that. So just like how with 5% heavy hitters, we only need 20 counters, kind of same thing going on here. Okay, so this is what I mean by saying, okay, allowing some approximation suddenly makes the problem much more feasible. Okay. Okay. But now, of course, the last issue then is that I don't know which ones to count a priori. I don't know that Nick Cannon is going to be very popular today. So, okay. All right. So, okay. I don't know if you guys saw it. Does anyone want to take any guesses at an algorithm before I reveal the algorithm on the next slide? Yeah.
I think you.
Yeah.
So I'm going to have like a window, sliding window, counts the frequency of the object in that window.
Oh, okay. So sometimes people are interested in sliding window kind of problems where you want to do like day by day or like last 24 hours. But we're not worried too much about that today. Actually, that would be a good homework problem. But we're not too. I'm just thinking of heavy hitters all time. Yeah, don't worry too much about particular time windows. Yeah.
I have a partial solution.
Okay.
I'm thinking of using hash functions, and we group, like we count each hash result, and since there aren't a lot of heavy hitters, chances are they shouldn't collide. So each hash index should correspond to one heavy hitter.
Okay, I think that's reasonably close to what's coming up. Then let's see. Okay, so here's what we're going to do. Again, we have a limited number of counters. Okay, so here what I'm going to do is I'm going to allocate, I guess, 10 over epsilon counters. I need at least 1 over epsilon, we think. So I over-allocated by a factor of 10. Okay. Now, ideally, I could say, oh, use this for the number 1 item and number 2 item, number 3, the biggest ones, right? But I don't know which ones are going to turn out to be biggest. Okay. So this is where we're going to use a hash function. And I'm just going to take all the elements and hash them randomly into different spots. Okay, so if there's 20 heavy hitters and I allocated 200 slots, I'm hoping that they'll be separated. And that each heavy hitter will be by itself. And then we have to account for all the other noisy elements running in, right? You're overcounting kind of everything. Okay, so that's basically the basic algorithm. It's not necessarily complicated. I allocate a few extra counters beyond the minimum, say 10 over epsilon, and I randomly hash the items in. So whenever this element appears once, then I go to that counter and I increase it by 1. And I don't know if this one appeared twice, I would increase this one by 2, stuff like that. And what makes it interesting is that if we have a collision, like this one has 4, then you get plus 4 down here, and altogether you now have plus 5, right? So the green is kind of getting dominated by the purple right now. That's the issue that we'll have to look at. Right? It's these collisions and understanding how much it affects our estimates. All right, so just to make sure we're on the same page, I left this as a rhetorical question. So if I'm running this algorithm that's sort of just hashing in the counters, and I wanted to get the estimated frequency of an element I, what would I return?
Divide the counter by how many things are mapped to it.
Oh, okay. I can try to divide the counter to how many things are mapped to it. Okay. So the suggestion was, okay, so let's say that, So let's work out our situation. So our situation, n looks like a billion or something, or 10, a gazillion, right? Whatever is a big number. And if we're doing 5% heavy hitters, 10 over epsilon looks like 200. Right? So the number of items that got hashed into one slot is a gazillion divided by 200. So you're going to take whatever counter, you're going to basically divide it by a gazillion.
So 0.
It's going to be awfully small. Yeah.
You take your counter and then divide it by the total length of the stream you encountered so far.
Oh, okay. Yeah, that's a simple one. We can just return A, HI, I guess divided by M if M was the length of the stream. Okay, I'm not going to lie. And for the rest of the notes, I realized that I just wrote it at AHI, which means I'm just returning the actual frequency, and implicitly we can divide by the length of the stream. But that's just how the notes are prepared up ahead. Okay, so this would just estimate the total frequency of IMI. Now, why intuitively, so let me ask this question. So the suggestion to divide is not a bad suggestion. I can see the intuition. But if we think about our application of heavy hitters, why is it maybe not so necessary to divide?
Most things are 0.
Yeah, you're kind of hoping that most of those things are 0 and that a heavy hitter will kind of dominate its counter anyway. And at some level, this happens in a lot of situations where you're trying to get the most important part of a lot of noise, or in the presence of a lot of noise, right? And so you don't really want to, say, divide in proportion to the amount of noise out there. So, yeah, we try to come up with different things. Okay. All right, so that's the algorithm. You just returned the counter. Okay, and you're hoping it's accurate for heavy hitters. It'll probably overestimate some of the smaller queries. But we'll figure out how to fix that too. Okay. All right, so does the algorithm roughly make sense? Okay.
Oh, question.
Yeah.
How do we know that, like, the element I is the heavy hitter of that hash index, and I is a noise?
We don't. But just in general, if you just say, hey, what's the count for I, you're just going to return A of I. And it may be wrong.
So it should be 0 is the correct, like return 0 should be the correct.
Yes. Yeah. We have not said anything about why it's correct yet, just establishing what we're going to analyze. And it certainly won't be, there's going to be lots of errors. As soon as you have any collisions, you're off by a little bit. Right? So, yeah. It's still interesting. Okay, so let me set up some of our notation. So I guess A1 through W, I use W for width, think of how wide it is, will be that array of counters. H will be the hash function, that whenever we sample. Fi refers to the frequency. I guess I'm using M for the total length of the stream. So for example, in this notation, the total value of AJ, the J counter, will be the sum over all the keys that hash to J, their actual frequency. All right, that will be our notation. And here then, I guess, is our one lemma. Okay, for all keys I, this is a claim. For all keys I, with probability at least 1/2, so I'm saying I'm going to be correct at least half the time. AHI represents our estimate for Fi, right? The claim is that our estimate is always at least Fi, and at most Fi plus epsilon M over phi. Okay, which is like epsilon over phi relative frequency error, because M is the total length of the stream. So the claim is that for any particular single, just one key at a time, I will get epsilon over phi relative error, or less, at least half the time. That makes sense. Okay. All right. So one side is a little bit easier than the other. Does anyone want to explain either one of the two inequalities right off the bat?
because for item HI will always go to that same counter, it has to be greater than that actual absolute.
Yeah, okay, so this inequality is kind of easy because AHI includes FI plus some others. Okay, so it's always an overestimate. In fact, that'll turn out to be very useful for us. So then, the interesting part to prove is the upper bound. Right? How come I'm not overestimating by too much? Oh, too often. All right. Does anyone, of course it's hard to say out loud a whole mathematical proof, but anyone want to take a stab at maybe some of the ideas that can get us there?
Markov's inequality.
Sure, yeah, but beyond buzzwords. Okay? So we are using a randomized algorithm, and there's hash functions, and there's Markov's inequality, and how do we set it up? What's the intuition? Is this surprising? Are you surprised? One person is surprised. No one else is surprised. Come up with something better next time. If you're not surprised, then why is it surprising? Okay, so let's see. If I rewrote this just a little bit, I'm just subtracting. This is, of course, the exact same claim. Right? Okay, well, what does this version say? This version says, so this represents how much I'm overcounting Fi. It's a non-negative quantity, we know that. So it's really saying, what is the sum of all these other things coming in? Okay. It's saying it's at most something proportional to m. Okay. Why? Yeah.
Universal hash function gives us a guarantee on the probability of the collision happening.
Yeah.
When
Yeah, okay, so we're hoping that not many things collide with Fi. Okay? And yeah.
I think the formula on the left is a random variable, and it's a combination of all the other elements' chance of hitting in Fi's self.
Yeah, so we're worried about other elements hitting in. The universal hash is on for one other element at a time, trying to say, oh, it probably won't happen too much, or at least it's an equal chance of being anywhere. In some sense. Right? Yeah, and?
So we know that the expected value of the frequencies added is just 1 over k is the length of the hash.
Yeah, okay, so k is 10 over epsilon, so it's roughly 1 over epsilon, right? So you're hoping that each other element has only like an epsilon chance of running into I. Okay? So what you see in this epsilon m is sort of like an epsilon fraction of all the other noise. Right, that's why we're getting kind of epsilon times m, is because our table is roughly 1 over epsilon. 10 over epsilon. Okay, so you're hoping that the noise from the other elements is sort of distributed evenly. Or at least if you're core number I, you're hoping that you don't get more than your fair share of noise coming in. Okay, the fair share of noise would be epsilon m over. All right, so let's look at the expected value. Okay. So if I'm looking at the average amount of overcounting, how might I proceed in my next step? Yeah.
The sum over all elements that look like
Okay.
and the probability and the frequency.
Okay, so let me write this out. So if I sum over all keys j, where hj is equal to hi, f of j. Okay, so this is the sum. I'm just writing out, I think, what we're all on the same page with. It's a sum over all their keys colliding with I, their frequencies. But that's only restating something that we've already said out loud. Now, how do I take the next decisive step? Because this is sort of a mess to analyze, isn't it? Okay, yeah, we only do one thing in this class. Okay. Okay, we're going to do linearity expectation. So, that's not how you do it. Okay. So I'll sum over all the keys. Now, when I'm summing over j, I actually don't know if it's collided yet. So I sum over j, and then I sort of the expected value of, what should I write? I'll write fj, and then I'll make up something, I'll call it, I guess, 1, and I'll write in the subscript hj is equal to hi. Okay, so this represents a random variable that will be 1 if hj is equal to hi, and 0 otherwise. I just kind of made it up, so is that confusing? Does that make sense? Okay. All right, so summing over all the keys, what's the expectation of, okay, if you collide, you get fj points, if you don't collide, you get 0 points. And again, now life is easy, because I can just look at one thing at a time. Okay. All right, so for a particular, which I guess, to put it further, is summing over j, the frequency times the probability that they collide. Right? Because if they collide, then you get fj, otherwise you don't. Okay. All right. And now what is this?
1 over k.
1 over k, what was k? Okay. And just to make it easier, this is at most epsilon m over 10. It's a little less if fi is non-zero, but it's probably pretty close. All right, so the average over counting is epsilon m over 10, at most. Okay, great. All right, but the claim was at least half the time is at most epsilon m over 5. Okay, Markovs. So Markovs, you apply it to some non-negative random variable x, right? What is our non-negative random variable x? Yeah.
Variable I minus
Yeah, actually, so this is important. It's actually the amount, because some people might say AHI. That actually wouldn't work. It's specifically AHI minus FI. And remember how we remarked that AHI is always bigger than FI because we're overcounting? So suddenly we're allowed to use Markovs. Okay, because it has to be a non-negative random variable for that, kind of 2 times the average argument to work. So that's a small subtle thing. Okay, so the probability of this being at least, here's our claim, right? Epsilon m over 5. Well, that's, on the right-hand side, we have 2 times the average. Right? And you can only be 2 times the average at most how often? Half the time. Okay, so, all right, so this actually just represents the average expected amount of noise coming in. You can see where universal hash functions are useful. And maybe it's key to point out that, linear expectation, of course, we kind of know it's important, but it put it in a, because, okay, what's the limitation of a universal hash function? It only tells you something about 2 items at a time. It doesn't tell you anything about more keys, right? But by the time I apply linear expectation, I've actually kind of reduced it to 2 items at a time. So you need linear expectation to get away with such a simple, fast, compact hash function. All right, great. Good job, guys. Okay. All right, so where are we? I've now shown that for any particular element, I have a good estimate of its frequency with constant probability. Probability 1/2. I'll get a good estimate for a particular element. But I want more. I want to estimate all the frequencies with very, very, very high probabilities. So I want to get all the frequencies, and right now I can I only have a guarantee for one element at a time, and it's only constant. Right? So what I want to do is I want to take what we've done and somehow put it on steroids, right? I want to amplify it. How do we amplify experiments? Yeah.
Can you just repeat?
Yeah. Yeah. Okay. So here's hope it's not. Okay. All right. Suppose you want to get heads, right? What are the odds of getting heads on your first coin toss? All right, half. So half chance you'll get tails. Yep. No good. All right. What about 2 coin tosses? What are the odds of getting 2 tails? 1/4. And what about 100 coin tosses? 1/2 to the 100. Of course, these are simple mathematical facts, but the key point is that it's decaying exponentially. As a computer scientist, you always want to keep your eye out for exponential growth. Right? That's really all we do. Okay, so what we're going to do is we're going to make D copies of our data structure for some parameter D. We'll figure out the suitable one in a moment. Okay. So there's one copy. There's 2 more copies. Another copy. I really went all out on this. Okay. There's D copies. Okay. And so for each one, I'll make a new set of counters and I'll sample a new hash function. So a deep hash function. So the total space is now looking like W times D at the moment. Okay. Times however much space a counter takes. Okay. All right, so here's a fun question. All right, so the idea of the algorithm then is an item comes in, I'm going to update D counters, each of which are just kind of assigned by the appropriate hash function. Fine. How would I look up an item? Okay, so if I want to estimate f sub I, and I have all these experiments running in parallel, what's the best way to get an answer? Yeah. Okay, average, that's a natural idea. You're hoping the average is well behaved. Any other ideas? Yeah.
Check if it's a heavy hitter in all of them.
Check if it's a heavy hitter.
If it's one of the heavy hitters or whatever, it always has to be mapped to the same one heavy value.
Okay, so I'll suggest 2 things. One, I am still interested in frequency of valid heavy hitters. But the other thing I think is that, so you said, okay, let's check to see if it's a heavy hitter in all of them. But what that will do, though, is now if one of these makes a mistake, like suppose one of these takes 2 heavy hitters and just puts it in the same one. That can easily happen, right? We only did 10 over epsilon, so it's like a 1 in 10 chance of this collision happening or something. So that means that one of these things screw up, you completely forfeit the heavy hitter. So you've actually, in some sense, put more stress on the data structure because now it has to be correct D times. I want to actually do something opposite, which is make it so that the data structure is not correct very often, but is correct enough, maybe a few times, to guarantee I get a good answer. Does that make sense? Okay. Yeah, you?
The minimum?
The minimum. So in our particular case, because we're always overestimating, the smallest number is the best number. So that is what we'll do. I won't bother writing it out, just... Okay. If I want to estimate f sub I, I'm going to return a minimum over my D copies. All right, so in what scenario does this not work?
What if it's a 0 and it's always in another heavy hitter?
Yeah, so in particular, this will be bad only if all the copies are bad. Okay, so if a single estimate is good, that'll give you a good minimum, right? That's the key. So now, as opposed to like kind of in your suggestion, these sort of all have to be correct. Now I'm saying we just want to make sure it's not all wrong, and only one has to be correct. That's much more to our advantage. Okay. So, did I write something? I did. Okay. All right. So this is a bad estimate if and only if all the hash counters over all copies are bad. Okay. Now, for a particular element I, what are the odds of all of them being bad? Yeah, that's the odds of it being good. Okay, so each particular one is bad was probably at most 1/2. So for them to all be bad, they're independent of each other. It would be 1/2 to the d. Okay. All right. So if I set d to be like 10 log n or something, where n is the total number of distinct keys, okay, then 1/2 to the d looks like 1/n to the 10. Right? And especially if we're interested in the astronomically large n regime, that's an astronomically small number to the 10th power. Right? Okay. All right. So we're able to put one element's guarantee on steroids now. Okay. But again, the question was, how do I guarantee all n elements are correct? Yeah. Union bound. Okay. So the key point is that 1/n to the 10 is so small that I can get away with a very sloppy union bound. Okay. So the probability that some element E is bad, that's what I don't want to happen. I don't want any elements to be bad, right? Is at most the sum over all the elements, the probability that E is bad. Right? That's the union bound. As simple as it looks, it's extremely effective. And so each of those is a 1/n to the 10 probability, and there's n of them. So we have 1/n to the 9. Right? If n to the 9 is not good enough for you, we could have made d 20 log n instead and have 19, etc. So you only have to increase that hidden constant, and everything goes down really fast. All right. Okay, so the total space, if I did d is equal to log n, and w was 10 over epsilon or something, comes out to log n over epsilon, and I have now an epsilon estimate for all the frequencies. Right, that's pretty remarkable, I think. What do I know? Okay. All right, so all put together. Oh, this is great. We're going to have time to do the high probability quick sort. Okay. All put together, we get these terms. Okay. And if you look back, the algorithm wasn't really that complicated either. It was log n over epsilon counters and just hashing n. That's very practical. Okay, any questions? All right, so the fun thing to think about, and I won't spoil it, is so all I've done here is shown for a particular parameter epsilon how to get plus or minus epsilon under relative frequencies. Okay, but the original question I started with was, can you identify all the heavy hitters? Okay, and so the question now is, how can you use this data structure to figure out all the heavy hitters online? There's no point in me saying out loud, you'll figure it out. All right. Fine. Okay. All right, so if you'll permit me to use the last 10 minutes to go over what I didn't finish last time, I'd like to. But you can always leave. I don't even know your name, so it's totally fine. Okay. Let's. All right, let's do this. Okay, so All right, so this was in the context of quicksort. Okay, so quicksort again, pick a random pivot, divide into two piles, recurse, right? And last lecture was mostly about linear expectation, and that's what we did. The key point was to set up these indicator variables, just 1 if they're compared, 0 if not, right? And then we applied linear expectation to separate out the terms. And then you have to do a little bit of thinking to figure out how to analyze one of these terms, but still it's much better than trying to analyze all these things together. And then we did some arithmetic. Okay. Get and log n. That's where we left off. Okay. So this will then, I guess, be our second example, having just done heavy hitters and seeing this occur, of getting a high probability bound. Okay, so last time we showed that on average it's going to take n log n time. That's good and probably already good enough in practice. But we will show that it will almost certainly be at most n log n. So I think we'll show that maybe the odds of doing more than 32 times n log n comparisons is 1 over n squared or something. Okay. All right. Okay, so how are we going to set this up? Okay, so all right, so for a particular element E, so maybe that's my input to start, and this is my element E. Okay. As the algorithm proceeds, it's going to kind of keep showing up in different subproblems, right? You might go to this subproblem, and E is somewhere in the middle, right? Okay, so a particular element is going to go through a string of subproblems until it gets chosen as the pivot, in which case it'll be done. Okay. So I'll call this the depth of the element E, the number of subproblems it participates in. Okay. Now, what the algorithm does, right, it picks a pivot and it compares to every other element in that phase. So actually, if you sum up the depths over all the elements E, you'll get the total number of comparisons. So sort of that adds 1 to the depth of E, and there's one comparison. This adds 1 to the depth of E, and there'll be one comparison corresponding to that E. So if I can bound the sum of depths over all elements, I'll get a bound on a total number of comparisons that's as good as the running time. Okay. So the claim is that for a particular element E, the odds of being at least 32 times, I just chose 32 to make some things convenient, 32 times natural log of n is at most 1 over n cubed. Okay. So we will do this, this will be most of the work. But why is this useful? Why does this roughly lead to the right bound?
It takes more than n log n very rarely.
Not quite, I don't think.
Medium boundaries to boundary also number of comparison is large.
Okay, so 1 over n cubed, the great thing of having n cubed is I can take a union bound over all n elements and have sort of like n squared left. Okay, so if I want to say, I want to make sure all the elements are less than 32 log n. Okay. This will be summing over each element, the probability that DE is bigger than that same quantity, which is at most n times 1 over n cubed. We have 1 over n squared still. Okay. That means that with probability at least 1 minus 1 over n squared, everything is less than 32 log n. So if I add them all together, we'll get n log n. Log n. Okay? Alright, so that means I just have to focus on the depth of one of these elements to finish the proof. Okay.
Is it the last or the name?
max, because I want to make sure they're all smaller, and I'm bounding a bad event. So I want to make sure the max is smaller than 32 log n, because that means they're all smaller than 32 log n. And I'm saying, what are the odds that the max is bigger than 32 log n? And that is small. Okay. Yeah. Although I often make that kind of mistake, so it's good to double check. All right. 5 minutes. Okay, so. All right, so we just have to analyze one element, so let's fix E. And as usual, the tough part is kind of setting up the right variables to look at. So what we're going to do is I've introduced these x sub i's, where x sub I is the number of elements in the subproblem containing E after I recursive calls. So x sub 0 is the initial. There's no recursive calls yet. So there's n elements. They're all there. Okay. And after E is selected as a pivot and there's no subproblem left, I'm treating x sub I as equal to 0. Okay. So in particular, the depth is at least I only if x sub I is greater than or equal to 1. And what we're going to try to argue is that xi is almost certainly less than 1, in which case for sufficiently large I, for I is something like 32 large. But to do that, we need to analyze the expected value of x sub I in 4 minutes. Okay, so, all right, how are we going to do this? Okay, so let's say x sub 0 is just n, all the elements are there. So x sub 1 is how many elements are remaining after just one iteration, right? So how many you get separated from. Now, if you want, you could probably calculate x1 exactly if you knew what the rank of E was. So if like E was at the very beginning, that would give you a slightly different number. Okay, but in any case, to do it exactly is going to be too painful, and I don't intend to do it. So here's maybe a lazier approach to get a weaker bound that'll be good enough. Okay. I want to call a pivot good if, say, out of 100 elements, it's one in the middle 50. Okay. So out of k elements, it's one in the middle k over 2. And one thing nice about that is that's enough to guarantee that at least 1/4 of the elements will be separated off from E. Okay, so no matter where E is, as long as the pivot is somewhere in the middle half, its problem size will be at most 3k over 4. At least k over 4 will get thrown out if you just think about it. Okay. And so that's good enough for us. Of course, the odds of being a good pivot is 1/2 because it's just the middle half of the elements. All right, so if I wanted to calculate the expected value of x1 in a somewhat lazier fashion, I can use conditional probabilities and say, okay, what's the conditional probability x1 given that you have a good pivot time plus conditional expectation of x1 given you have a bad pivot. Right? Now, if you have a good pivot, you're going to get to throw out at least 1/4 of the elements, no matter what. Okay, so we'll have 1/2 times 3/4 n here. And if you choose a bad pivot, well, I'll just be lazy and say, okay, well, at the very least, there's n left in the next subproblem, right? I won't get any points. So I'm just doing a lazy overestimate. But that's still good enough to say, okay, on average, it's at most 7/8 n. So I'm making some progress on average. Right? If you made 7/8 n progress every time, then you would, in log n depth, you'd be down to 0. Right? But you don't necessarily get it every time. So we could do the same thing for general i's. Okay, so I is 100. So conditional on whatever is there after 99 rounds, you would still get, okay, 1/2 of the time you get a good pivot, in which case it would be 3/4 times whatever was left after I minus 1 rounds. Remaining part of the time, you just say, oh, I don't make any progress. All right, 7/8 xi minus 1. So this is only a conditional one because you need to know the value of xi minus 1. But whatever the value is, it'll be at most 7/8 of it. All right, so why is this useful? All right, so Intuitively you're thinking, okay, on average you go down 7/8 of the time, so after 10 rounds I should go down 7/8 to the 10. And that's true, but to show this, it's not as straightforward as, say, applying linear expectation. Because this is doing multiplication, not addition. Okay? But we can use a trick that was introduced last lecture, and we never used during the lecture, which was this law of iterated expectations. Okay? So we'll do it inductively on I. So let's say I've already established this for x sub I minus 1, that it's at most 7/8 to the I minus 1 times n. Right? Okay. So we can write it like this. Nothing has actually changed. Okay? So I sort of randomly sample xi minus 1 first, and then I look at the conditional expectation of xi given xi minus 1, which is something we do know how to analyze. Okay? This is what we just showed. This is the kind of good pivot type of thing. Right? And by induction, the expected value of xi minus 1 is 7/8 to the I minus 1 times n. So we get 7/8 to the I times n. Okay? Just a little math. Almost done. Late again. Okay. But in particular, after 32 log n of these iterations, I'm not sure if you guys know this inequality, but you need to. Okay, 1 plus x is less than or equal to e3x for all x. Okay, I'll put it in the homework or something at some point. For this particular choice of k. So whatever, it's going down geometrically. You're doing log n iterations. You're going to get poly n, 1 over poly n. Right? As usual. Okay. Okay, so now I'll let you guys do the finishing touch. I want to argue that the odds of xk being at least 1, which means that E is not done yet, is really, really small. Okay. So I want to bound the probability that xk, for xk is some constant times log n, is at least 1. Because if it's less than 1, that means that E is done, right? The recursive subproblems have ended. All right, so now for this last step, how can I bound? The usual shout-out buzzwords is not a bad strategy. Okay, if we use Markov's inequality, average is like 1 over n cubed, right? So 1 actually represents n cubed times the average. Okay, so actually the odds of it being at least 1 is at most 1 over n cubed. Okay, so the depth is at most 32 log n, was probably 1 over n cubed. Okay, and then that completes the proof, and we're done. And now we never have to speak of it again. Okay, thanks guys, and I'm here for questions as well as office hours.